In this video, I want to look at the graphs of the sine and cosine functions. Let's start with the sine, so y equals sine theta. Well, to do this, we're going to rely on what we know sine is from our given unit circle values or our special triangle, however you find those exact values for the pi over 4, pi over 3, all of those. I'm going to rely on the ones that give me exact values. So there's a few I know very easily. Sine of 0 is equal to 0, so I get that point right there. I know sine of pi is equal to 0. I know sine of 2 pi also equal to 0. I know that at pi over 2, I get the whole value of 1. And I also know that these aren't going to be straight line paths, because if we think about pi over 6, it's equal to 1/2. But then pi over 3, it's slowing down its rate of increase to equal to the root 3 over 2. So it's not increasing at the same rate. It's not just shooting up the whole time in a straight line and coming back down, same idea. So we're getting a curved path from the 0 to the pi. At 3 pi over 2, we have our -1. So we have the same idea where we have that curved path to get down there. Try and even that up. It should be symmetric on both sides, just we have our positive or negative. And so this is what one wave of the sine function would look like. Remember, the period of sine is 2 pi, because 2 pi gives us that full rotation. After one full rotation, we get back to those same unit circle values, or the same special triangle values. We can think of it also in terms of coterminal angles. So 2 pi would give us a full wave, one full wave, and I think it's easiest to start at 0 because why not? But we should keep in mind that we can continue to grow more and more and more, but we run into all of those same values. At, say, 3 pi, we'd have the same value as pi, 4 pi is 2 pi. If we were to look at 5 pi over 2, that's the same as pi over 2. So sine is an infinite wave. It just continues in the same pattern over and over again, just keeps going forever and ever, both in the positive and the negative direction. All these would be the same. So when we're drawing the sine wave, going to be asked to either show one period of the sine graph or maybe a couple wavelengths, right? This is also called a wavelength. One full sequence of sine values. We don't have to show this positive one. We could show the negative one as well, but this is just an example of one we could show, and I think it's the easiest one to show. But we should keep in mind it is continuous. So if we're asked to graph the full sine function, that'd be impossible, right? We'd have to show that it continues with some arrows, show that it continues on that same path. Cosine, let's look at the cosine next, and then we'll talk about how we can move these things around. I think about it in terms of those same values. So I know at 0, cosine actually starts at 1. And 2 pi later, 2 pi being coterminal with 0, we get back to the same value of 1. If we look at pi, that's where we reach the -1. And with cosine, at the pi over 2's, we have our zeros, our x-intercepts. So we have our 2 points here and here. And so connecting those, I would have this pattern here. And notice on the sine, I never overshot those marks. Here I overshot them just a little bit, so I've gone just past the period. I always do that because I have the hardest time coming up to those points and indicating a turn if I don't actually start from below. So what I mean by that, just to kind of indicate on this point, if I were to go between these two, if I don't continue over here to the left, a lot of times when I try and connect them, it kind of makes it look kind of straight. And so to really indicate that it does turn there, I will start just beyond it to really help myself out in drawing that to see that it does curve down there. It should curve at both of those points. But not necessary if you can do a better job drawing than me, which is not particularly hard. I will point out that these do look the same, and if I was to extend this down in the same way we said sine just continues on and on, cosine continues on and on and on, we don't have to draw it if we're going to just show that one wave, but they do look the same. They are identical, other than the fact that it's just been shifted over by that little bit of distance right there. Cosine started that pi over 2 units off, and remember with the cofunctions, we said that we could relate sine cosine through a shift of pi over 2. And so once again, we see that pi over 2 difference, just like we saw with the cofunction identities. And just like with the sine, we can say that our period is 2 pi. It takes a full 2 pi to complete our wave. There's something else that we can define right now, which is the amplitude. The amplitude is the wave height. When we're looking at the wave height, we do not look from the trough to the peak. We don't look from the low to the high. We look at what I call the level watermark, right? If we didn't have a wave, if it was flat, right? If the wind stopped blowing and the wave settled down, it'd be right here at 0. So from 0 to our peak, or from 0 to our trough, how much is that? And in both cases, the amplitude of our wave is 1. Here, the amplitude 1 as well. So these terms are going to help us when we go to shift these things around. So let's talk about all the things that could shift. Let's start with the sine wave. Now, if we remember transformations from earlier math classes, we've probably seen something that looks very much like this, but instead of sine, you might have seen f of x representing the function. A, B, C, D, we know these are all just transformations, and then we can sprinkle some negatives in there too. We'll get to those in just a minute. But let me stick with the A, B, C, and D. From before, we should remember that A is what we call the vertical shift. So, not vertical shift, sorry, the vertical stretch. So if we think about stretching these things vertically, what that is changing is how high and how low we get. What that's changing is this new term, it's the amplitude. So the amplitude, I'm going to abbreviate AMP, we find that by the absolute value of A, and I'm throwing that A inside an absolute value because if A is negative, that doesn't cause a negative amplitude. Amplitude is always a measure of distance, so it is positive. Amplitude is going to be given by that A. Before we didn't have a number in there, which is why it's just a 1. The B affects the horizontal stretch. So remember, anytime anything's inside the parent function, or inside, in this case, the sine, that means that it will be doing the opposite. If it's attached to the x, it's the opposite. And so if we see that b is something like, say, 3, that's not going to be stretching it. That's actually going to be condensing it. We would think, hey, multiplying by 3 would make it bigger. It does the opposite. It's going to condense. And so if we think about condensing along the x-axis, that is changing this aspect right here, the wavelength or the period. So we can find our period by taking our standard period, or the 2 pi, what we had before, and dividing it by the b. Just like with the amplitude, period is a measure of distance, so I'm going to put that b in absolute values. The c is going to shift the function left and right. It is what we call a horizontal shift. But we're going to give it a little bit more of a special name this time. What we saw with these sines and cosines, they're infinite waves, right? They just kept going on forever and ever. So it doesn't make much sense to say it's a horizontal shift, because if it's infinite, right, and if it has the same pattern here as it did here and as it will here, well, what does it mean to have a horizontal shift? We're going to rename this slightly. We're going to call it the phase shift. And you'll see me abbreviate this PS just to write it a little bit faster. And we get this by taking negative c over b. We'll see an example of how this plays in, but why are we taking the negative c? Well, we already said the x's are backwards, so we have to use the opposite sign. And then why are we dividing by b? Well, again, we're not treating it perfectly as that horizontal shift, because remember when we did order of operations with our transformations, we said we had to apply the horizontal shift first. I'm not moving in that order here. So to correct for the fact that I didn't correct the horizontal shift first, I'm dividing off that b the same way I kind of divided into the period here. Then finally, the d, this is what we called a vertical shift from before. It would move us up and down. It's still going to be a vertical shift. Or you'll see me abbreviate it BS. And so we shift d units up or down. Depending on if it's positive or negative. So that one's exactly like we've defined it before, because it doesn't continue infinitely up and down. Vertical shift makes a lot of sense to use that terminology. So let's take an example, and I should note too that I've done this all with sine, but it would work the exact same if I had switched this with cosine. They're going to be exactly the same, which makes it really easy, and that's why we can study them together. A negative here we know reflects it across the x-axis, a negative here would reflect it across the y-axis, so those are the same as before. Let's take an example. Let's take the equation y is equal to 3 sine 2x minus pi over 3. So we got a lot of different aspects here. Let's just start by defining it all first. I think that's the easiest thing to do. Pick out all your elements before you ever try to do the graph. So I see that 3 sitting out front. Like we said before, that is affecting the amplitude. Our amplitude would be equal to 3. The period will be equal to 2 pi divided by the b. Our b was 2, and so we get just pi here. And then the phase shift, that's our negative c. So we had a negative. I'm going to have a negative negative. It's going to end up turning into a positive, pi over 3. And I have to divide that by the b, which was 2. So I have a negative negative pi over 3, which turns into positive pi over 3. Divided by 2 is pi over 6. So I have all the key elements now. I need to sketch this thing out. When I do my graph, I'm going to always start with that phase shift. If we're shifting the thing around, it doesn't make much sense to say, hey, the highest point is here, because it's going to shift left to right. The pi over 6 is going to be the first point I draw from. And when I'm choosing which points to shift from my sine and cosine, the original ones we defined up here, it is always easiest to start with the thing at 0, because that is unaffected by any stretch or compression. So I'm going to start by moving what we said sine was at 0, which is 0, to pi over 6. From there, I'm going to go out a full period. I know that the period was pi, so I need to go out a full pi units to get to the end of the wave to complete a full cycle. So this point here is not at pi, because we started at pi over 6. I have to take pi over 6 and add pi. That'll give me 7 pi over 6. Halfway in between them, I know that halfway in between them, sine has to reach 0 again. That's going to be our third x-intercept for pi, for sine. So if I think about what's halfway between pi over 6, 7 pi over 6, I'm just finding a midpoint. So adding the two, I get 8 pi over 6, and then if I take half of that, I get 4 pi over 6, which is the same as 2 pi over 3. I need to figure out those highest and lowest values, which we said before were 1 and negative 1. Well, our amplitude's 3, so we're going to have to change that to 3 and negative 3. And I know they're going to occur here and here, but I need to define where those are. Whenever I ask you guys to graph sine or cosine, I want to see all 5 points that we did in the basic sine and cosine. And I want to see what their x values are. I want to see what their y values are. So we need to figure out the halfway point between these two. This is pi over 6. This was 4 pi over 6, remember? Pi over 6 plus 4 pi over 6 is 5 pi over 6. If I take half of that, it's 5 pi over 12. I do the exact same thing here. 4 pi over 6 plus 7 pi over 6 is 11 pi over 6. Taking half of that, 11 pi over 12. And so again, you might need to refresh a little bit on fractions here, but we do want to be comfortable adding, subtracting these fractions pretty quickly and then dividing by 2 when we need to. So connecting my points, this would be my one wave of the sine function. And they should be curves, not v's, but I've done my best. We want to make sure that it is proportionally correct. So pi over 6, a little bit to the right of the y-axis. We wouldn't want to show it over here or way over here. We want to have all those x values labeled, all those y values labeled. Notice we're ending up with that same pattern. It's just been shifted a little bit, different peak, different trough, things like that. Let's take one more example. Let's take y is equal to negative 2 cosine of x over 3 and then plus 2 on the outside. So parentheses are very important. We want to pay attention to where things are with respect to the parentheses. Let's start with the amplitude. The amplitude, remember, is the A. So I see that negative in front, but I'm going to ignore it for right now. The amplitude will be 2. The negative will cause a reflection over the x-axis. Next, I'm going to move on to the period. Period is 2 pi divided by the b. Well, the b here, it's over 3. The x is over 3, meaning there's a coefficient of 1 here. 1 over 3 is my b, meaning I'm going to have a period of 6 pi. My phase shift, there's none. There is no c here. My phase shift is going to start the same place it usually starts. Cosine starts at its max at the point 0, 1. But I do have a vertical shift of 2. I'm going to have to go up by 2. And then, like we said, I'm going to take note of that negative there. That negative is going to give us a reflection over the x-axis because it's in front of the function. So let's put this all together. So no phase shift, that makes it a little bit easier. I'm actually going to ignore this vertical shift, and really let me treat that last. I'm always going to do this vertical shift last, the same way we should with our just any other transformation. So let me ignore that for right now. I'm going to draw this thing as if that wasn't there. So if we have a cosine graph that has an amplitude of 2, no phase shift, we'd say, hey, it should start up here at 2 because there's no phase shift. But remember, we reflected about the x-axis, which means it starts down here at -2. That will be my first point. The period is 6 pi, meaning 6 pi units later. I have to complete my wave, so it will get back to that -2. Halfway in the middle at -3 pi, that will be where it's reaching its max, and that max will be +2. Halfway between each of those at, I said a -3 pi, I don't know why I said a negative, it should be a +3 pi. Halfway between 0 and 6 pi is 3 pi, but what that gives us is the negative version, which switches back to the positive version, the +2. And then finally, let's look for the zeros. The zeros will occur at the halfway points, or the 3 pi over 2. Halfway between 0 and 3 pi is 3 pi over 2. Halfway between 3 pi and 6 pi, add the 2 together, 9 pi, and then divide by 2, 9 pi over 2. So notice we're starting on the wrong side of the x-axis. That's expected because we had that reflection going up, coming back down, and then that would be one full wave. Again, I overshoot it just a little bit because that helps me get the rounding right. Notice I still didn't do it exactly right over here on the right-hand side. I've gone below where I needed to be. So let me try and clean that up a little bit. Should be more like that. That looks a little bit better. But the reason I did all this in blue is because I didn't do it correctly. I didn't take into consideration that vertical stretch. So I think the easiest way to do this is to go ahead and just shift these points after I have it drawn. Draw that first one, indicate to me in some way that this is not my final graph, right? I cross that through, that's clearly not my final. Now what I'm going to do is I'm going to take all these points and shift them up by 2, putting that in black so I can see the distinction. Goes up by 2, that goes up by 2. That will actually go up to 4, extending out my axis a little bit messy. It's hard to draw on the screen. So it goes up to 4. That one's going to 2. That one's going to 0. Now I'm going to connect the dots. But remember now that this is really kind of that level watermark. And if you want to put that dotted line through it, that sometimes is helpful to remember that that should be where the things are kind of bending about. So I'll have a graph that looks like this, just shifted up by 2. It should look identical to the blue underneath of it. It's just that it's been shifted up. And so we've taken into consideration now everything. So I want to mark this as my final graph. You can write final next to it or call it y, write out what it is, y equals blah, blah, blah. So hopefully we have a pretty good idea now how to graph the sine cosine function.